Good morning, friends. Today in this class, we will discuss on the sampling process. We will look into confidence interval. Then we will have a discussion on the confidence level. And then we will look into an example to determine the confidence interval. And finally, before we wind up, we will have a look at the Bootstrap sampling. And also we will look into the Python code that can be used to verify the Bootstrap sampling process. Okay, and let's begin with the sampling process. I understand that we discussed on the sampling process in the last class. I have given you a pictorial representation on the right side of the screen, wherein you have a representation of the sampling process, like how it has been done. Okay, like if you look over here, the population is going to be very huge, so we can't study the whole of the population. So you take a subset from the population. Okay, and then you start to study about that particular sample and determine the statistics for that particular sample. And the sample statistics is referred to as like the characteristics. Okay, and example for the sample statistic would be your sample mean, which is denoted by x bar, and sample standard deviation, which is denoted by s. Okay, these are all referred to as the characteristics for the sample. And after you determine the statistics, you tend to infer the population parameter, right? So the population parameter, it could be a mean, which is denoted by the Greek symbol mu, and the population standard deviation, which is denoted by sigma, right? This is the whole sampling process. Okay, in short, you won't be able to study all of the data. You take a small data set, study the data set, and measure the characteristics for that particular small data set, which is referred to as statistics, and use that statistics and infer the population parameter. This whole process is referred to as sampling process. Let's look at an example. Okay, like what I have given below is an example. Okay, over here, what I have here is, let me zoom it a bit so that you can look at the chart in a more clear way. Okay, so if you look here, I have a normal distribution. The bell-shaped curve that you see here is a normal distribution. And the population, so this represents the whole of the population, and the population mean is 100, and the standard deviation, which is nothing but the line that you see on the right side and the left side of the center, right, is referred to as the standard deviation. This represents your first standard deviation. Okay, this would be your first standard deviation, and this is going to be your second standard deviation, so on and so forth. Okay, so basically this whole curve is your normal distribution curve. This whole thing is a normal distribution curve, which is an inverted bell-shaped curve, Gaussian curve. Okay, and the mean of the population is found to be taken as 100, and the standard deviation, which is nothing but the distance of a point from the mean. The center point is referred to as a mean. Okay, the standard deviation is going to be 1. Okay, so each and every standard deviation, right, you can put it as 1. Okay, this is what we have in that particular example. And what I have done is I have taken some random samples. Okay, and then I have taken 99, 100, 101, and 102. There are 4 elements in this particular sample, and the mean comes to about 100.5. If you look carefully here, the mean for the population is 100. The mean for the population is 100, whereas the mean for the sample is not 100, it is 100.5. There is a difference. Ideally, it should match, right? If you look at the above process, what we had said is we try to infer the population parameter using the statistics that you determine using the sample, correct? But if you look here, the sample data doesn't match with the population data. The sample mean doesn't tie up with the population mean. Correct. So how do you address this? Okay, so this is basically an issue, right? So basically I won't be able to infer anything about the population, because let's say that I take a different sample, and then again it will show me a different mean, and then using that I may not be able to infer anything for the population, right? So the reason this is happening is because of the error, right? Because of the sampling error that we discussed earlier. And the elements that go into the formation of sample is not the complete representation of the population. It is not the 100% representation of the population. That's why you tend to have this particular difference, right? So how do you overcome it, right? So if you look here, what we have done is we have given you a point estimate of 100.5. Okay, this is basically a point estimate, which means that this number this number is this is an exact number. This is one single number which is given, and you're trying to project this for the population, which is not correct. So instead of that, what we tend to have is that we tend to have a range. Let's say that I will have a range. Okay, and this range, if I represent anything using a range, it is going to be more helpful, and then it is going to be more accurate, right? That's where the confidence interval comes into picture, right? The confidence interval is nothing but a range of values within which your population parameter would lie, right? If the population parameter that we're talking about is not certain, we're not sure about it, right? When there is uncertainty, it is always good to refer it in a range of value, right? That's what you're referring to as confidence interval. So basically, I have given you the definition over here. Confidence interval, a confidence interval is a range of values within which we are sure our true value, the true value is nothing but the population parameter lies in. Okay, and if there is anything, if you're trying to estimate something which is you're not certain about, don't give point estimate. Point estimate should not be given if there is a lot of uncertainty in the data, right? It's always good if you go for the range estimate. Okay, so this is always good. Okay, so that's what confidence interval is. Now let's look into confidence level. Okay, so understand here there are two different terms which I'm talking about. One is confidence interval, which we just discussed, and the next one is confidence level. Okay, so these are two different terms. Okay, confidence interval is nothing but a range. Remember, it is nothing but a range of values that we're talking about, right? And your population parameter will lie within this particular range, right? So it is used to quantify uncertainty, right? That's what your confidence interval is all about. But if you look at confidence level, there are certain predefined confidence level which statisticians use. One is going to be your 90%, the next one is going to be 95%, and the next one is going to be 99%. Okay, so these are all the common confidence levels which statisticians use. So what is the confidence level? We discussed in the last class that when you take a sample, I get I get different values, right? Because the sample is not complete representation of the population. S1 would give you a mean of 50, and S2 could give you a mean of 48, and S3 could have given you a mean of 45. So I see a lot of variation in it, right? So this would lead to a lot of confusion when I tend to infer certain thing for the population, right? So I tend to lose my confidence because every time when I try a different sample, I get different information and I can't use it, correct? So how do I get the confidence, right? So you need to express certain things in confidence. So that's what the statisticians have come up with. That's a different term called confidence level. What it does is that if you express something in 95% confident, it means that if your confidence level is 95%, it means that if I repeat the same experiment 100 times, out of 100 times, in 95 times, I would definitely get the same value that I got before, and then the population parameter will definitely lie in this particular range that we're talking about. Okay, so this is what a confidence level is. The confidence level, it gives you opportunity wherein you can project or infer certain things for the population with confidence, right? So that's what I have written over here. The interpretation of the confidence level is that we are 95% confident that the population parameter lies between X and X, which is nothing but the two different values, right? Those two different values are considered to be one over here and another over here. Okay, so let me repeat that again. Confidence level, it basically comes into picture because of the sampling error that we have. S1, S2, S3, these are three different samples, and they have given you three different means. One time, once you got 50, the second time you got 48, and the third time you got 45. The reason is the elements which goes into the sample are different. Now I don't have the confidence to infer certain thing for the population. So in order to infer things for the population with confidence, the statisticians have come up with confidence level. The confidence level commonly used numbers are going to be 90%, 95%, and 99%. Okay, and the confidence level of 90% implies that if I do an experiment 100 times, if I take 100 different samples, and out of those 100 different samples, 95% of the time I will get the same value, or I can say that 95% of the time the population parameter would lie between certain different values, certain values for certain number of times. Okay, so the certain values is going to be the range, right? That we got using your confidence interval formula, right? So that's what the confidence level is all about. Okay, now let's go into the method by which I can determine my confidence interval. Okay, so I have given you the formula which goes into the determination of your confidence interval. The confidence interval is given by this formula. It is denoted by x bar plus or minus of z into s divided by square root of n. X bar is sample mean, okay, and z is your confidence level value, okay, and which means that you tend to determine it using your z table, okay, like uh, based on the confidence level that you select, 90% or 95% or 99%. Okay, based on the value that you select, you need to go to the z table and then look at the corresponding values to get your z values. And standard deviation, that is something that you should be having it when you're trying to determine your confidence interval. And n represents the sample size. Okay, so this formula is fairly simple. Like it's basically like talking about your sample mean and then standard deviation, the number of elements that you have in the sample, and then the z value determined based on the confidence level that you're selecting. Okay, so over here, if you look over here, what we have done here is that we have about 4 points, correct? So 99, 100, 101, 102. There are 4 elements, correct? So the number of elements is 4. And the standard deviation, if you look above, it is going to be 1, and the population mean is 100 and the sample mean is 100.5. okay, so I have taken that over here. The population mean is 100, the sample mean is 100.5, and the confidence interval which I have selected is 95% confident. Okay, now when I go to the z table, okay, and which I will let you know shortly, right, how to look up the z value using the z table. Okay, based on this confidence interval, we get a z value of 1.960. okay, so this is something that you get based on the z table. The z value is something which is coming from z table. Okay, so basically we know this is something that based on the observation, right, based on the number of samples that I'm trying to take, right, and I will definitely have an idea about what the population standard deviation is. The population mean, I have information on that, and the sample mean also I have information on it. Right, now we need to just substitute all these values in the formula. Right, when you substitute all these values, what you get is the confidence interval as 100.5 plus or minus 0.98. okay, so what it is giving you, it is giving you a range. Okay, so this particular value that you see here is giving you a range, and the range is between 99.52 till 101.48. correct, so this is giving you a range. Okay, like so, and if you look at this range, the population mean of 100 definitely lies in this range, right? So which means that whatever information that you inferred, right, using the population mean, right, using the sample is going to be like in this particular range of 99.52 to 101.48. okay, so this is what the confidence interval is. This is how you can determine the confidence interval. Okay, let me go through it again so that you have a clear understanding. Confidence interval is given by x bar, which is a sample mean, plus or minus of z, which is your z value, into s divided by square root of n. N is the sample size and s is the standard deviation for the sample. Okay, now all you have to do is you have to substitute the values in it, and then you will get a confidence interval. And the confidence interval that you get for the above example is 100.5 plus or minus 0.98, which means that the confidence interval range is between 99.52 to 101.48. If you look at this particular range, the population parameter, the population mean, which is 100, definitely lies in this range, right? So that's what we discussed about. Confidence interval is all about a range of values within which the population parameter will lie, right? So it does satisfy the definition, right? That's what the confidence interval is all about. Okay, Now there is one more example which I have taken here. This again I referenced from a different book. Okay, like so there are about 40 randomly chosen men, and we are measuring the height of those men. The exercise is to measure the height of the population, which is pretty huge, right? So I take 40 random sample of men from that particular population, and I find that the mean is going to be 175 centimeter, and the standard deviation is going to be 20 centimeter. Okay, so the mean formula, we know that mean is given by you sum all the elements divided by the number of observations. That's your mean, which is given over here. And if you want to know how to determine the standard deviation, it is given by the formula over here, which is nothing but s equal to square root of summation of I equal to 1 to n xi minus x bar the whole square divided by n minus 1. Xi is the observation, the point, the observation that you are factoring in. X bar is going to be your mean, right? And n is going to be the number of observations, the number of points that you are studying, right? So all you have to do is that you have to substitute all these values, and then you will be able to get information on the standard deviation. Okay, so this s represents the sample deviation for the sample. Okay, that's why we have n minus 1 coming into picture. And we also know the confidence interval formula, which is given by x bar plus or minus of z into s divided by square root of n. Okay, so now we know all these values, right? So based on the question that you have here, you would be able to write these things. These things are pretty straightforward. Okay, like this value you already have, which is 40. X bar also you have, right? And standard deviation is also given. Okay, and all you have to do is that you have to plug in those values, and the z value, right? I guess that we have taken 1.960, which is 95%, right? This whole information is coming from z table, and it's always good if you remember these values. These are all common values which gets used, right? You need not go to the z table to look up these values, right? So for 95%, 1.960 is the z value, which corresponds to 95% confidence level, right? So that's what gets substituted over here. Okay, and just by substituting, what you get is that you get the answer is 175 centimeters plus or minus 6.20 centimeters, right? So this is what you get as a confidence interval. Now let's look at one more information. Okay, like that is something like pretty easy, and to you have to know it, right? This plus or minus of 6.20 is the margin error. Okay, that's what I mentioned over here. The value after plus or minus is called margin of error. The margin of error is an example. This example is 6.20 centimeters. Okay, x bar, this is your x bar value, which is your sample mean, right? And then you're adding some value just to buffer in your error, so that like your population parameter, your population value will lie in that range, right? So that's how you determine your confidence interval, right? So basically what we have done here is we have discussed about what confidence level is, and then we discussed about what confidence interval is. Okay, and before that we discussed few information with regards to the sampling process. Okay, and then we looked into two different examples, one with 4 data points, and the next one is we have taken one more example wherein we are trying to use the data pertaining to the height and determining the confidence interval, right? Now this is an important interview question, right? So which you can expect. Okay, like if you read the question, how will increasing the confidence level from 95% to 99% affect the confidence interval? So here I'm talking about confidence level, here I'm talking about confidence interval, and what I'm talking about is I'm increasing my confidence level from 95% to 99%. Okay, let's look at this using a simple example. Okay, let's consider that this is a small hole and this is a very big hole. Okay, and you're trying to throw a stone into this hole, like which one do you think, right, will have more probability to catch it, right? This is going to be very low, wherein this is going to be very high, right? So the same thing happens over here, right? So here you will have more confidence, right? Your confidence will be very high that the stone that you throw will definitely flow or definitely will fall into this, whereas here you will not have so much of confidence, right, the confidence is going to be very low, right? So basically what happens is when your confidence level gets increased from 95% to 99%, right, your confidence interval size increases. Okay, so when your confidence level increases, right, this is your confidence level that I'm talking about. This is your confidence level. This is your confidence interval. Okay, when I want to express something with more confidence, it means that I need to have a wide big bucket, right? The confidence interval will increase. Okay, like, so this increases. Okay, so that's what that's the answer for this, right? So basically when you increase this confidence interval, what it means is that your margin error also increases. Okay, so your confidence interval, which is nothing but the range, which is nothing but which is expressed as x bar sample plus or minus of your margin of error, right? Margin of error, right? So this particular value increases, and because of that, right, your confidence interval also increases. Okay, that's the answer for this one. So basically, let me read it for you. Increasing the confidence level means one are more likely to capture the means we are more likely to capture the true value, which is nothing but the population, with each interval, right? To be more confident, we use wider intervals with a larger margin of error, right? That's what I meant, right? So basically what happens is, again, I'm repeating, when the confidence level increases, right, when it increases from 95% to 99%, your bucket, which is nothing but like confidence interval, the size of the confidence interval increases, so does the margin of error. Okay, that's the answer for the above question. Okay, now let's go to the next topic, which is about bootstrap sampling. Okay, this is something interesting. This is an interesting topic. We will try to verify it using Python code as well. Okay, this is one of the sampling technique that we have right here. What we do is that we will measure using a sample. Okay, and after you measure it, we will put the sample back into the old bucket. Okay, and then again we will take the sample and repeat the process again. Okay, it is a method, wherein like I will be able to infer the population parameter more accurately. Okay, and this is one of the best methods, or widely commonly used method in order to infer a few things for the population. Okay, not only for the population but also for other statistical algorithms, we can make use of bootstrap sampling. Okay, so basically, let me explain this with an example. Okay, let's say that we have a school and there are about 1,000 students in the school. Okay, and I do not have the time or the resource to measure all the 1,000 students. Okay, so what I do is that instead of looking or studying all the 1,000 students, I take a sample of 5 students and I measure the height of those 5 students and find the average. Okay, this is going to be sample 1, S1. Now what I do is that I repeat the same process again. Okay, which means that I again take a different sample. Now what I will do is that I will put all these 5 people back into my population. Okay, these guys will go back into my population. Now I'll take another random sample of 5 students. Okay, measure their height and again determine their average height, and that will be my S2. Okay, likewise I will repeat this process based on my convenience or based on my statistical knowledge. Okay, let's say that I'm repeating the same process 20 times. Okay, which means that I have S1, S2, S3 and so on and so forth till S20, and each and every sample has got 5 elements. All these elements, all these samples will have 5 elements. Okay, and each and every time I would have determined the average. I would have determined the average of S1, I would have got the average of S2, I would have got the average of S3 and so on and so forth till S20. Okay, so I have got 20 different averages. Now what I will do is that I will again take an average of all these 20 points. Okay, this is what you have to do, right? And if you look at this, right, and if you look at the final result that you get here, right, whatever value that you get over here, right? The final sample value that you get here, the sample statistic that you get over here, this will be more close to your population. Okay, so this will be very close to the population. Okay, so what I'm saying is that I have a school, okay, and there are 1,000 students studying in the school. Okay, and I don't have the time or the resource to measure all 1,000 students, so I take random of 5 students, measure their height and find the average height. Okay, that's sample number S1. Now I put these 5 students back into the population and pick again another sample, and then I take about 5 people and then I measure them, get an average, and then I keep it separately, right? That will be sample S2. Likewise, I repeat the same experiment for 20 number of times, which means that I have got about 20 different buckets having 5 elements in them. Okay, and I also have the average values, which means that I have average for sample S1, average for sample S2, and so on and so forth till average for sample S20. Now I take an average of all these values put together, right? And if I look at the final value that I get, it will be very close to the mean of the population. Okay, here what I'm doing is that I'm not measuring all the people who are there in the population. I'm just taking a subset, repeating the same experiment again and again. Okay, and then I'm finding the average, right? And if I look at the final sample value that I get, it will be very, very close to my population. And this is one of the best methods by which I can infer certain parameters for the population. Okay, so let's look at what code has been written in Python. I guess that we already went through the Python classes before, so I need not explain in depth. But still, again, I will just brief you through the code. Okay, so we know that these are the libraries, right? That you over here. These are the libraries that you import from the Python, and then I have given you the definition for a random.normal, which have what happens and what are the parameters which goes into it, and what is the definition for that, right? So basically, the first 3 lines that we have here, they are the libraries that we are importing, right? And we are using random.normal function. Okay, this function gets used, correct? So I have given you given you the syntax or the definition of random.normal. There are 3 different parameters which goes into it. LOC is nothing but your mean, and there is scale, which is your standard deviation, and size is nothing but more like the shape of the array that you're talking about, or the number of elements which goes into it, right? That's what I would explain over here. Okay, so and we are forming a normal distribution, that's why we have put in normal, which comes in over here, right? So basically, first 3 lines, they are the libraries which which we will import for any kind of coding that you are trying to do here, for the stats and for the algorithms, right? These are the basic libraries that we import, right? And then I have given you the definition of random.normal. What it means is that I'm trying to generate a normal distribution, okay, and it is coming from the NumPy library, right? That's why we have put an np.random.normal. Okay, and it's going to pick in random values, and it's going to pick in, and it's going to form a normal distribution. Okay, and if you look at the normal distribution, the mean is going to be 500, which is being mentioned over here in this line, right? And the standard deviation is going to be 1, and the sample size, or the distribution is going to be like 10,000. Okay, and what we're doing is that we are finding the mean. So this will be my population. Okay, so this line talks about the population, and I'm finding the mean of my population over here. This is the mean of population that I have found. Okay, and the mean value comes to 500.008. Okay, so let me again refresh. Sorry that I'm repeating again for you guys, so that you don't you don't have any kind of doubts. First 3 lines talks about the library, the standard libraries that we import, and then we form a normal distribution. In that normal distribution, I have used np.random.normal. Random, it used to pick up random information, and normal distribution is what I need. I have given information about what is going to be my mean and standard deviation and the data points which goes into it, right? And if you look at the next line, which is np.meanx, it's going to find the mean for the population, and I got an output as 500.008. Okay, so population is taken care now. Okay, now let's look into the sample. Okay, so basically we need to have 40 samples, each having 5 elements in them, and then we have to find the average of them. Okay, and after that we have to find the average of those 40. Okay, so there are two different activities which gets done over here, correct? So let's look how the code is written over here. First thing is that I'm forming an empty list, right? Sample.mean, and this is nothing but your empty list. Okay, and after that, like, I'm forming my buckets, right? 40 buckets are required, so that's what I'm forming over here. And then what I'm doing is that in each and every bucket I need random values of 5, right? And I'm putting that in the list which has been represented over here, right? And after that, what I'm doing here is that I'm finding the average of each and every bucket which gets formed, right? That's what is written over here. Okay, so first is that for I in range 40, it means that I need 40 buckets to be formed, and then I'm specifying that how many elements to be needed, how many elements we need, right? That's what I mentioned over here, random.sample, and I'm converting x.toList in, I'm converting this information that I have in x, which is nothing but your population, right? This is x is going to have it's a variable which holds the population, and I'm taking 5 elements from it and I'm going to pick random values from it. That's what this line of code is talking about. Okay, and after that I'm finding the average for those 5 elements, storing it in the variable called avg. Okay, and that's what that's what the first 3 lines are doing. And if you look over here, this empty list which I've created before gets appended over here with that average value. Okay, that's what is the 4th line of code is doing over here. Okay, it's very simple. The first thing is that the libraries which we know. After that, I form a normal distribution. Okay, I specify the mean, and then I specify the standard deviation and specify the number of elements which goes into it. I find the mean of the population, and then I do the process, the actual process, wherein I need 40 samples to be taken. So that's what this line of code is doing. And then I take 5 samples, 5 random samples, right, from the population. That's what this line of coding is doing. And then I find the average, which is the 3rd line of code, and the 4th line of code is nothing but like appending those average values into my empty list. Okay, once that is done, finally what I do is that I print, or I find the mean, I find the mean of those 40 different entries that I have in this variable called sample underscore mean, right? That is what is being done over here. Okay, now if you look at the output, right, that you will get something which will be in the range of 500 point, one second, let me do this calculation, 500.0024. Yeah, so this is what I get. Okay, now if you look here, this is your sample, right? This talks about the sample. Okay, the information that you get from the sample, and the value that you see here, which is highlighted in a different color shade, is coming from the population. And you see that these 2 values are pretty close by, right? They are almost the same, right? So this is one of the best way by which you can infer the parameter for the population. Okay, so this is the practical implementation of Bootstrap sampling using Python code. And let's look at some of the observations, right? That we get, right? The first line, it talks about how close your population and sample values are, right? We see that they are very close by. That's what I have mentioned in the first line. And if you look here, like so it is actually comparable, right? Your sample statistic is actually comparable with your population parameter, and you don't really need to spend a lot of time resource in looking at all the entries in your population. You just took some sample, and then you are able to get you're able to get or infer the population parameter more effectively, right? That's your second point. And this gets used in random forest, okay? And even if you have a very small size, and if it is if the sample size is determined or formed using bootstrap sampling, then the random forest tend to give a very good performance. Okay, so these are all the benefits that you get by using bootstrap sampling. One is that whatever information that you infer, right, about the population using your sample statistic, it is going to be comparable, it is going to be very close by. The second point is that you don't have to spend too much of time to measure all the population parameter. Okay, like the computation requirement is very less over here. You just take a sample, repeat the same experiment again and again, and finally you get your sample statistic. Okay, and then in random forest, if you tend to employ, or if you tend to form your samples, or if you tend to make use of bootstrap sampling, even with a sample size which is going to be very small of 20%, you will get a very good performance. Okay, so with this, I think we have covered almost all the topics which I had planned for today. Okay, so let me revise what we have went through. Okay, first thing is that we discussed something on the sampling process. I think this is the third class on which we are discussing again on the sampling process, but still, like, it's important, right? So we discussed on how sampling goes, and then we discussed on the confidence interval, and then we discussed on confidence level, right? So these two things are not different. Again, please do bear that in mind. Confidence interval talks about a range of value, whereas confidence level is more like a percentage, right? With what confidence level can you project the population parameter, right? With what confidence can you say that your population parameter will lie between certain values, right? For a certain for a certain amount of time, right? That's what your confidence level is all about. Then we found the statistical way by which you will determine your confidence interval, right? We saw two different examples. Okay, and after that we went into the bootstrap sampling, where we discussed how bootstrap sampling works, wherein, like, you look at the population, you don't measure all the population, but you take a sample, you measure the height, and then determine the average, and then you repeat the same processes again and again for different samples, and every time when you repeat it, you put these sample elements back into the population. Okay, and then you repeat it again and again. This is your bootstrap sampling process, right? And we also looked at how this could be verified, or how I can, right, validate my theory about the bootstrap sampling. For that, we made use of Python code, right? It's a fairly simple code. I guess that people who have covered my Python class, they would not find it very difficult to understand the above lines of code. Anyways, we went through each and every line of code over here, and then, like, we finally concluded with observations, right? With this, I would like to conclude this class, and we will again come back next week, and then we will discuss on few more important topics related to statistics. Okay, and these classes are going to be continuing at least for another 1 to 2 months, the stats classes, and then we will go into machine learning algorithms. Thanks, guys. Thanks for being patient, and I hope that you guys have got the crux of this particular session. Have a great day. Thank you. Bye bye.